I'm super excited to be here and welcome everyone to this session. Today, I'm going to talk about redesigning scheduling in Array to improve the cost efficiency and scale. So a little bit about myself. My name is Jia Jun. I'm currently a software engineer at Anyscale. I'm working on Array core with a particular focus on the scheduling part. So today, we will go through the following outline. First, I will give a brief overview of Array scheduling, and then I will talk about some unique scheduling challenges of AI applications. And then I will deep dive into two AI applications. One is the cost-efficient model serving, and another is large-scale data preprocessing for distributed training. And then show how Array scheduling can make them run faster and cheaper. Finally, I will conclude and talk about some future works that we're planning. So first, let's talk about what Array scheduling is. So at a very high level, Array scheduling is finding a node to run a task or actor while satisfying the scheduling constraints. So let's take a look at one example. So here, I want to schedule a task that requires one CPU, and it takes an object as an argument. So by doing that, this task actually specifies two scheduling constraints. So the first constraint is a hard constraint, which is the num CPU equals to 1 resource constraint. And since it's a hard constraint, the node that can run this task must satisfy this constraint, meaning that the node that must have at least one available CPU. So because of that, the first node is ruled out for scheduling considerations because it doesn't have available CPUs now. The second constraint is a soft constraint. So here, we prefer to run the task where the object is to avoid data transfer. And the soft constraints, they are nice to have, or they are nice to be satisfied, but they are not mandatory. So since the only candidates to run this task is the second node and the third node, and both of them cannot satisfy this soft constraint, the scheduler then is free to pick either of them to run the task. So let's say in this case, the third node is picked to run this task. So now let's look into more details on how the scheduling protocol works. So again, it's still the same task that's to be scheduled. So the first step of the scheduling protocol is that the driver, the application driver process, will try to request a worker process from the distributed scheduler of the locality favored node. So here, the locality favored node is a node that actually has the objects that's needed by the task. So in our case, it's actually the first node that you can see it has the object in its local in-memory object store. So driver will request a worker process from that node's distributed scheduler. So this is the first step. Given the first node, it doesn't have any available CPU resource now. So it will ask the driver to try another node that it thinks has available resources. So driver then tries to request a worker process from another node as suggested, as recommended by the first node. In this case, let's say it's the third node. Since the third node has available resources, so it can satisfy the hard constraint, so it grants a local worker process to the driver. After that, the driver sends the task to the granted worker process to actually run it. So this is the whole protocol of how you can schedule a task. So now let's look at the actual actor scheduling. So actor scheduling is also very similar, but with a key difference that we will see later. So the key difference is instead of the driver requesting the worker process directly from the distributed scheduler, it actually asks GCS, which is a global control service, a single process that's running on the header node that manages the entire kind of array cluster. It asks GCS to do so. This is needed so that GCS can actually manage the lifecycle of actors and implement features like detached actors. So that's kind of the key difference. Except that the remaining processes are basically the same. So GCS tries to request a worker process from a random node's distributed scheduler. So let's say it picks node 2. Since node 2 has available CPUs, it can grant a local worker process to GCS directly. And then GCS will send the actor to the granted worker process to run. So this is the protocol for actor scheduling. It's pretty similar to task ones. So to summarize, race scheduling is basically trying to find a node to run a task or actor while satisfying the scheduling constraints. So here, scheduling constraints, it has kind of two types. The first type of scheduling constraints, we call it like hard constraints. Those are the constraints that must be satisfied in order to run the task. And the classic example is resource constraints. And the second type of constraint, what we call like soft constraints. Those are the constraints that are nice to have, but not mandatory. And the example, for example, is like data locality constraint. So another important thing is like we use a decentralized scheduling architecture. So what that means, like every node runs a distributed scheduler that can make the scheduling decision independently. And also, every node has resource views of other nodes so that it can tell the driver like where to ask for worker process if it locally cannot satisfy the constraints. So this decentralized design avoids a kind of a single scheduling bottleneck that you may have with a centralized scheduler, and make basically the scheduling like horizontally scalable. So next, let's look at the scheduling challenges of AI applications. So the main challenge we will discuss in this talk is the kind of the diversity of scheduling requirements. Different applications, they have different requirements, which leads to different scheduling solutions. Just to give you a sense, so here are two AI applications. Like one is model serving, and another is data preprocessing for distributed training. Let's look at their requirements and the scheduling solutions that's needed. Later on, we will discuss them in more details. So for model serving, the first requirement is like high availability, which is obviously needed for online service. And the solution to achieve that is we want to having a cross availability zone spread scheduling. And the second requirement is low cost. And we want to use spot instances to achieve low cost while handling the spot instance preemption gracefully. So for the second application, data preprocessing for distributed training, the first requirement we want to discuss is high throughput. And we need solutions like spreading those data preprocessing tasks and collocating preprocessed data with trainers. And another requirement is like high stability. And we have like out-of-memory prevention to improve the entire system stability. So because we need like different scheduling solutions to meet those kind of diverse scheduling requirements, Ray developed like several scheduling features, such as like node draining or node label-based schedulings. We will go through those features one by one in details later, but this just gives you a sense. Okay, so now let's deep dive into two AI applications and show how Ray scheduling can satisfy their unique requirements and make them run faster and cheaper. So the first is a cost-efficient model serving application. So here, model serving, I mean, basically serve like machine learning models or large language models using Ray serve library. So it has two requirements, as I already mentioned before. So the first requirement is high availability. So why we need high availability? Because like as an online serving system, it needs to run 24/7 without downtime. However, like hardware failures are norm rather than exceptions, as you already know. And you can have like disk failures, network failures that happen every day. And those failures can kind of impact availabilities. And even worse, like availability zone failures can also happen, for example, due to like natural disaster like earthquake, or you may even have like just simple human errors. And we need to make sure that we still have high availability of the system even when those failures happen. So the second requirement is low cost. Why we want low cost? Because like model serving is actually expensive, especially you want to serve those like large language model. To give you one example, for example, if you want to serve like Llama 2 70 billion models, you actually require like 4 A100 GPUs. which is roughly around like 11,000 per month if you are using, let's say, on-demand AWS instances. So it's quite expensive. If we can bring down the cost, you can have more users. So now let's see how rescheduling can help to meet those requirements. So for model serving, what we want to schedule are called like things are called replicas. So each replica is an actor that can serve some model. And you have and a serve application, you can have multiple replicas for fault tolerance and also for like horizontal scalability to support like higher QPS. In this example, let's say we have like 4 replicas that we want to schedule. So let's see how we can schedule those 4 replicas to meet the high availability requirement. So in order to be highly available, like we want to run replicas in multiple availability zones, so that even though let's say one zone is down, we can still have replicas in other zones to continue serving traffic. So to schedule replicas in multiple AZs, we need to first launch RAID nodes in multiple available zones, and then set the correct AZ node labels. So here, the node label is a new kind of experimental concept that's introduced to RAID in 2.7. And basically, a node label is basically arbitrary key-value pairs that describe a property of a node. So this is very much the same as like a Kubernetes node label concept. So here, in our example, let's say we launched like three nodes, like 2 in US West 2A and 1 in US West 2B. So after now, we have nodes in different availability zones. Next is to like spread those replica actors across availability zones. So we will use the node label-based scheduling to achieve that. So in this code example, we create a replica actor with the node label scheduling strategy. And the strategy is basically saying, like, hey, I want to run the replica on a node that's in availability zone US West 2A. So we will use this strategy to schedule the first 2 replicas. So as you can see, they run on the first 2 nodes because they are in US West 2A. And for the last 2 replicas, we want to schedule them in US West 2B. So you can see the node label scheduling strategy is changed a little bit. So it's in US West 2B. So these 2 replicas, they are scheduled as expected to the third node. So now the replicas, they are spread across AZs. So when, let's say, US West 2A is down, we can still have like 2 replicas in another AZ to serve traffic. Hence, we can have higher availability through this way, which is nice. So OK, so now we achieved high availability. Now let's see how we can achieve low cost as well. So the solution is to use spot instance. So what are spot instances? Spot instances, they are actually unused capacities in the cloud, and they can be like up to 90% discount compared to on-demand prices in AWS. So it's very cheap, which is the thing we want to lower the cost. So, however, like while spot instances, they are cheap, they have their drawbacks. They basically have lower availabilities. They can be preempted at any time by the cloud provider to reclaim the capacities. And the consequence is that if you have any requests that's currently being handled by the replicas on the preempted spot instance, those requests will all fail. So in our example, let's say on the second node, there's a request running on replica 2. And once the spot instance is preempted, the request will fail, which is like bad to the end serving user. So how can we solve this? So how can we, the question is, how can we have the benefit of those cheap spot instances without paying the kind of the low availability penalty? So the solution is like handling spot instance preemption gracefully via a RAID feature called like node training. Let's see how it works. So basically, when, like they say AWS, as an example, it decides to preempt a spot instance, it will actually send you a kind of preemption kind of notice 2 minutes in advance. So give you some time to prepare. So upon receiving the notice, the read node will transition into a state called like training state. And this means like no new tasks and actors will be scheduled onto this node because we know this node will be terminated soon. So while this node is in the training state, reserve will actually wait until all the existing requests on the training node to finish. In the meantime, it will guarantee that for all the new coming requests, they won't be routed to the replicas that's on the training node. Now, let's say after a while, all the ongoing requests on the training node have finished. The next reserve will stop. In our case, replica 2, that's on a training node, and it restarted somewhere else. Since rescheduling guarantees that no new tasks and actors can be scheduled onto the training node, so the replica 2 actor ends up being scheduled onto the first node. And finally, let's say after 2 minutes, the node is terminated by AWS. But since we have finished all the ongoing requests on this node and migrated off all the existing replicas, so no requests will fail when we terminate node 2, which is good, what we want. So just to show a graph. So this graph shows what happens if we don't have this graceful spotted instance preemption feature. So this graph shows the number of failed requests over time. The x-axis is the time, and the y-axis is the total number of failed requests. As you can see, initially it starts button, it starts with 0 because you don't have any failed requests. But once spotted instance preemption happens, you can see a bunch of requests actually fail. So in contrast, if you enable the graceful spotted instance preemption feature, you can see the number of failed requests remains 0, even though when spotted instance preemption happens. So to recap, for model serving, we implement cross-AZ spread scheduling for high availability requirements. And the scheduling feature we are using is the node label-based scheduling. And we also implement graceful spotted instance preemption for low cost, so allow you to safely use spotted instance through the node training feature. The second application I want to talk next is large-scale data preprocessing for distributed training. So this diagram shows the high level of data processing for distributed training. So here there are 2 array libraries that's involved. So we use array data to load and pre-process training data, and then use retrain to actually train the model on GPUs. So there are 2 requirements we want to achieve. So the first requirement is high throughput. Why high throughput is needed? Because nowadays, training data volume is huge. It can be terabytes or petabytes. So high throughput is basically a must-have if you want to finish your pre-process within a reasonable amount of time. Right. Second requirement is high stability. Given the data volume and the nature of data preprocessing, it's kind of a memory-intensive workload. So it has a higher chance of out of memory compared to other applications. And the high stability means the system shouldn't randomly crash or hang due to WOM. Now let's see how rescheduling can help to meet these 2 requirements. So here, what we want to schedule are those pre-processed tasks. Each task loads and pre-process a partition of training data. And the pre-processed data will be routed to those training actors, we call the trainers. And in this case, we have, let's say, PyTorch trainers running on the GPUs. They are waiting for the pre-processed training data. So in order to achieve high throughput, we want to spread those pre-processed tasks across nodes in the cluster for load balancing. And the way you can do it is using the spread scheduling. So this is how you can do it in code by specifying the spread scheduling strategy. So after that, Ray will try to spread those tasks kind of in a round-robin fashion. So let's take one example. So you can see, OK, so here the task 1 is scheduled onto the first node, the task 2 is scheduled onto the second node, the third task go back to the first node, and the last task go to the second node. So as you can see, through this way, pre-processed tasks they cannot be spread across all nodes, so the load is balanced. So after pre-processed tasks are spreaded and executed, the pre-processed data, basically the output of those pre-processed tasks, they will be saved to the local in-memory object store, where the pre-processed task run. So the next step is to route this data to trainers so that we can, and we want to collocate those pre-processed data with trainers. So if we don't have collocation, we may route pre-processed data to the remote trainers, which will have the extra data transfer cost, and it is slow, which will kind of affect throughput. So these two red lines actually shows those kind of bad routings to remote trainers. So to avoid this, we want to use the object location information to route those objects to the closest trainers. And in read data, we implement some special, what we call a split coordinator actor that basically tracks the locations of all these pre-processed objects and also the locations of those torch trainers, and they try to match them so that each torch trainer receives local objects without any kind of data transfer across nodes. So now we have high throughput. Let's see how we can achieve high stability through the UM prevention. So let's first see why UM is bad for stability. So here we have two tasks running on the first node, and let's say the task one is using too much memory, causing the So when happens, let's say the Linux killer will try to kill some processes and to free up the memory. The issue is that it's not guaranteed that the operating system killer will kill those task worker processes. So if we are unlucky, the killer might kill the RAID system processes and bring down the entire RAID node. Or even if you are even unlucky, then it may kill, once the GCS process is killed, the entire RAID cluster is done. We want to avoid that. So to avoid that, we developed a component called memory monitor, which is essentially an application-level killer that kicks in before the operating system one. So it runs on each node, and it can continuously monitoring the node memory usage, and it tries to kill tasks if the node memory usage is above some configured threshold before the OS killer kicks in. So this way, Ray can control what processes to kill, and Ray has kind of the best knowledge to pick the best one to kill. So here, let's say in the example, task one is killed. So after task one is killed, task two continues running to finish, and then task one is retried automatically. And at this time, since there's no task two that's also consuming memory, so task one has enough memory to run to finish, so it can succeed. So as you can see with our memory monitor or application level killer, the application can run successfully without So to recap, we spread data preprocessing tasks through the spread scheduling and collocate preprocessed data with trainers through the locality-aware routing. Both are for the high throughput requirement. And for the high stability, we implement prevention through the RAID memory monitor. So to conclude, different AI applications, they have diverse scheduling requirements, and RAID provides different scheduling features to meet these scheduling requirements. So in this talk, we have covered node label-based scheduling, node draining, spread scheduling, locality-aware routing, and the RAID memory monitor. So finally, I want to discuss some future work that the RAID core team is thinking about. And if you have any future requests around scheduling, feel free to reach out to me as well. So the first thing we are thinking about is tent and toleration. This is, I think, it's a concept from Kubernetes, and we want to kind of bring into RAID. So this can be used, for example, to allow you to avoid running those kind of CPU-only tasks on the GPU nodes, so you can save those GPU nodes for like GPU tasks. The second thing we are considering is like multi-tenancy. So like you can as an organization, you can allow users to share a kind of single large rig cluster, and this should be able to like improve the hardware utilizations. And because of multi-tenancy, we also need like a stronger resource isolations so that workloads from different users, they won't kind of interfere with each other. And the last is like a multi-cloud rig cluster. So you can have one rig cluster, and you have nodes from different cloud providers, so that, for example, one use case is like user, for example, can leverage those very cheap GPUs from special cloud like Lambda Lab or CoreWave. Yeah, so this is basically pretty much my talk, and thanks for attending. I think we still have some time for questions.
Thank you. That was a great talk. So for the preemptible option that you put in, is it also going to be available for Google Cloud Service?
Sorry, can you repeat your question?
So for the preemptible option where you're actually monitoring and you get the alert from AWS 2 minutes before the preemptible node gets pulled, are you going to have, is it available for Google Cloud as well, or is it just AWS currently?
For both Google Cloud, but this is kind of currently the Anyscale proprietary feature, but it supports both AWS and GCP. Yeah.
Thank you.
Thanks for the talk. This question on the multi-tenancy support, how far is that in your roadmap?
So the question is about talking about the multi-tenancy support. Yeah, I think that's something like we are thinking, and we want to like learn from the communities to see like what your kind of requirements for multi-tenancy, so that we can better design it. But that's something like we are considering, and then we have heard from different users. They like want us to support this, but we want to make sure we kind of collect enough requirements so that we design it right, so that can like meet your kind of requirements. So yeah, we should definitely talk like offline.
Hi, I have questions follow up about the preemption notification. So is that specific logic done by the reserve, or like is also public API exposed to the user, so they can capture the signal and do some kind of drawing logic?
Yeah, so the recall underlying support is generic. Currently, like basically it will provide signal to the layer applications, tell you, hey, this node now is in the training mode, so you should migrate to your workload of this node. So currently it's integrated with Reserve, but it can be used by other applications or your own application as well.
Yeah, so let's say if I'm running on my custom private cloud, I have a custom node provider, I do need to implement that kind of signal capture by myself, right? Or like
yeah, if it's your own cloud, you need to catch it and basically tell us, hey, this node will be.
I see. So another question is about the node, the memory monitor. So that piece is still also internal pieces within like relates, right? Or yeah. I think it's a very good idea. So for example, I probably want some kind of like local node monitor, customer node monitor. For example, I want to check the GPU health status or like some kind of other health metric about the nodes, and can hook up into the relate. And the relate will also take that basically the monitor and decide if this node is good or not, or if the process is good, is healthy or not. Is there going to be exposed more like custom API for this kind of monitoring?
Yeah, currently we don't expose like allow you to plug in different monitors, but that's something definitely we can discuss and see. Yeah.
This will be the last question. So great talk, thanks. I have a question about so Ray Core has different type of scheduling strategies, right? So do you have anything like to benchmark for each type of workloads, which scheduling policy is the best for that particular type of workloads, or you really just depends on the users to select the scheduling policy for their own applications, or any best practices?
Yeah, so normally like if you are using like high-level array libraries, you don't need to deal with these scheduling things. Like it's completely like hide from you. So if you, for example, use rate data and the retrain, you don't. This is more like internal data. Internally, you spread and do the data locality aware like routing. But if you want to use Recore directly, yeah, then you need to pick that fits your need.